In this video, we're going to see polar plot of a transfer function with a pole at origin and two simple poles. If you look at the transfer function of such system, it will be 1 over s times 1 plus st1 times 1 plus st2. Okay. For polar plots, we substitute s equals j omega. So let's substitute with j omega in place of s. The transfer function looks like this: 1 over j omega times 1 plus j omega t1 times 1 plus j omega t2. If you take this in polar form, which is magnitude and phase angle form, this equation will become 1 over omega times square root of 1 plus omega square t1 square times square root of 1 plus omega square t2 square. Okay. And the phase angle will be minus 90 degrees minus tan inverse of omega t1 minus tan inverse of omega t2. Okay. We can write this in complex form too. Okay. If you write this in complex form, this equation will look like this. We have this equation, okay, 1 over j omega times 1 plus j omega t1 times 1 plus j omega t2. In order to get this equation in complex form, we multiply this with the complex conjugate of the denominator term, okay, in the numerator as well as denominator. This will be minus j omega times 1 minus j omega t1 1 minus j omega t2 whole divided by the same term, okay, minus j omega times 1 minus j omega t1 times 1 minus j omega t2. And if you do the derivation, okay, the final result looks like this: minus omega square times t1 plus t2 divided by omega square times 1 plus omega square t1 square times 1 plus omega square t2 square. Okay. And the imaginary value looks like this: omega cube t1 t2 minus omega whole divided by omega square times 1 plus omega square t1 square times 1 plus omega square t2 square. Okay, this is the real value and this is the imaginary value. Now we have two forms of this equation. One is polar form, which is magnitude and phase angle. The other one is complex form, which we have real and imaginary values. Now let's start taking the values of omega and let's see what is the magnitude and phase angle. Now when omega is 0, the magnitude term m, if you look at this magnitude equation, if you substitute omega equals to 0, m will come out to be infinity. And phi will be minus 90 degrees because omega t1 term will be 0 and omega t2 term will be 0. Tan inverse of 0 is 0. Okay, so we have phi being minus 90 degrees. And if you take values, if you take value for omega to be tending to infinity, then the magnitude will tend to be 0, because if you substitute this omega tending to infinity in m, we'll get this value to be 0. And if you look at the phi value, if you substitute omega tending to infinity in this term and in this term, we'll have tan inverse of infinity as 90 degrees. So we have 3 times 90 degrees. It will be minus 270 degrees. Okay. So if you look at this tabular form, if you change omega from 0 to infinity, the m value, the magnitude value, is decreasing monotonically, and the phase angle is also changing monotonically from minus 90 degrees to minus 270 degrees. Now we know that m is infinity, but we don't know what is the value of the real axis and imaginary axis as omega tends to 0, which is m tends to infinity. To get these values, we can look at this real value and imaginary values of this function. If you look at this and the substitute omega equals to 0, we'll get the values for it. Now suppose see the real value. Okay. Now omega square gets cancelled. If you substitute omega to be 0 in this equation, we will get, I'm writing it here. Okay. It looks minus t1 plus t2 is the real value. And if you take imaginary value, okay, if you take omega square here, okay, then cancel it at this places omega square. If I cancel it here we'll have omega left over, and here if we cancel we'll have 1 over omega. When we substitute omega 0, the denominator becomes 1, and the numerator, this term becomes 0, and this term will be infinity. So we'll have minus infinity. Okay, we have minus infinity. We can write this as minus of t1 plus t2 minus j infinity. We have both of these values, real and imaginary values, to be negative. So we are in the third quadrant, okay, while drawing this. And phi value also indicates minus 90 degrees. Fine. And if you look at the plot, if you try plotting this in a complex plane, okay, let's say this is real axis, this is imaginary axis. Now let's take a reference line, okay, like this, and magnitude of this, or this point, is minus of t1 plus t2. So this magnitude of difference from origin to this point is t1 plus t2. Now when omega equals to 0, m is infinity, so taking a very high value for the imaginary axis in the negative direction, it will be tending to this value in real axis, okay, and in imaginary axis it will be infinity. Okay, so we take these values, and now when omega is infinity as shown here, okay, m is 0 and the angle is minus 270. Minus 270 line is this, okay, this j omega axis line, and 0 is here. We take this value. So from looking at this, it is spanning over two quadrants, that is from quadrant number 3 to quadrant number 2 it is going, and it is going to 0, and it is having some value here. Okay, if we try plotting this, it's a continuous plot, by the way. The plot looks something like this. Okay, it tends to this value, but the arrow mark directions will be in this direction, because this is the value for omega equals 0, and this value is when omega tends to infinity, and we mark the arrow directions in this way because as omega tending from 0 to infinity, the corresponding value should be arrow marked in that direction. Okay, this is how the plot looks, and this is the magnitude. Now we want to find out what is the magnitude of this particular thing. Before that, we need to know what is omega at this point. Omega equals question mark. Okay, now let's find out this omega. This omega we write omega at minus 180 degrees. Okay, now we take phi, we know the equation, which is equal to minus 180 degrees, which is equal to minus 90 degrees, minus tan inverse of omega t1 minus tan inverse of omega t2. We can cancel minus signs here and subtract 90 from 180. We'll get 90 equals tan inverse of omega t1 plus tan inverse of omega t2. We saw this equation before. Okay, if you take tan at both sides, we'll have infinity equals omega t1 plus omega t2 over 1 minus omega square t1 t2. Okay, now if you take this, the denominator should be 0, because we know omega is not infinity. Okay, we are taking value somewhere in between 0 and infinity. Okay, now 1 minus omega square t1 t2 should be equal to 0. So omega equals, we'll have plus or minus 1 over square root of t1 t2, but the omega minus 180 degrees in this case is 1 over t1 t2, which is plus. This is the equation. And now if you see the magnitude at that particular value of omega, we have magnitude as omega times square root of 1 plus omega square t1 square times 1 plus omega square t2 square. If you substitute this, we'll have 1 over, okay, 1 over t1 t2 square root of omega square, so we'll have 1 by t1 t2, so t1 cancels, so we'll have t1 by t2 square root of 1 plus t2 by t1. If you rewrite this equation, we'll have t1 t2 over, oops, t1 t2 over 1 plus t1 plus t2. We'll get this equation. Okay, now if you plot that polar plot again, we have this magnitude, value, we have this phase angle, okay, minus 180, at which we know the frequency. So if we redraw that polar plot, we have this value set already. This is t1 plus t2, and the plot looks something like this, right? And it extends to infinity, and the arrow marks are like this, right? And this is the magnitude we are referring to. This magnitude equals t1 t2 over t1 plus t2, and the omega at this equals 1 over square root of t1 t2, and this is when omega tending to infinity, and this value is when omega equals to 0, which is infinity. Okay, this is the polar plot for a function which has a pole at the origin and two simple poles, okay, 1 plus st2. So this is the polar plot. We have seen a polar plot for a function which just has two simple poles in the previous videos. So at the end of this polar plots, we will see how it is going to be affected if we introduce this pole, okay, at the origin. We'll see this when we complete polar plots.